The universe is filled with countless stars and even more planets, many of which lie in the habitable zone where life, as we know it, could potentially thrive. This brings us to a profound question posed by physicist Enrico Fermi. Where is everybody? If life is so abundant, why haven't we detected any signs of extraterrestrial civilizations? The Fermi paradox essentially highlights the contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for or contact with such civilizations. Our Milky Way alone contains over 100 billion stars, many of which host planets in their habitable zones. Given the age of the galaxy and the number of potentially habitable planets, it seems statistically likely that intelligent life should have arisen elsewhere. Yet, we observe silence. This silence raises questions about the conditions necessary for life and, more specifically, intelligent life. One possible explanation for the Fermi paradox is that the conditions required for life, particularly intelligent life, are far more stringent than we have assumed. The emergence and sustenance of complex life may depend on a series of rare and interdependent conditions. In this documentary, we'll explore how plate tectonics influence a planet's ability to support and sustain life. We will examine Earth's unique geological features, compare them with our planetary neighbors, and discuss the implications for the search for extraterrestrial life. By understanding the critical role of geology in habitability, we may find that the rarity of plate tectonics is a significant factor in the Fermi paradox. One of Earth's defining features is its dynamic geology, driven by plate tectonics. But what exactly are plate tectonics, and why are they so crucial for life? Plate tectonics refer to the movement of large plates that make up Earth's surface. These movements create mountains, cause earthquakes, and play a vital role in regulating the planet's climate by recycling carbon through volcanic activity. Plate tectonics are a fundamental aspect of Earth's geology, involving the large-scale movement of 7 major and numerous minor plates that float on the semi-fluid asthenosphere beneath the lithosphere. This process is responsible for many geological phenomena, including earthquakes, volcanic activity, mountain building, and oceanic trench formation. The concept of plate tectonics revolutionized our understanding of Earth's dynamic nature and its ability to support life. Furthermore, plate tectonics contribute to the recycling of essential nutrients, such as phosphorus and potassium, which are vital for life. The constant renewal of the planet's surface through tectonic processes ensures that nutrients are continuously cycled and made available to living organisms. Without this renewal, life-sustaining nutrients would become locked in rocks and sediments, rendering the planet less hospitable. On a broader scale, plate tectonics also create diverse and complex habitats. The formation of mountains, islands, and ocean basins through tectonic activity generates a variety of ecological niches, promoting biodiversity. These diverse habitats provide opportunities for different forms of life to evolve and adapt, leading to the rich tapestry of life we see on Earth today. However, the presence of plate tectonics is not a given for all planets. Earth's tectonic activity is driven by its internal heat, generated by radioactive decay and residual heat from its formation. This heat creates convection currents in the mantle, which drive the movement of tectonic plates. For a planet to have plate tectonics, it must possess sufficient internal heat and a composition that allows for the formation and movement of lithospheric plates. The presence of plate tectonics on Earth may be a rare and fortunate occurrence. If plate tectonics are essential for the development and maintenance of complex life, then planets without tectonic activity would be less likely to host advanced civilizations. This rarity could help explain why we have not yet detected signs of extraterrestrial life, despite the vast number of potentially habitable planets in the galaxy. To understand the uniqueness of Earth, we must compare it with its planetary neighbors. Venus and Mars, despite being in the habitable zone, do not have plate tectonics. Venus, with its thick, toxic atmosphere and extreme surface temperatures, has a stagnant lid, meaning its crust is a single immobile piece. Mars, smaller and cooler, lacks the internal heat to drive tectonic activity. Venus, often referred to as Earth's sister planet due to its similar size and proximity, presents a stark contrast in terms of geological activity. Despite its potential for habitability in the past, Venus currently exhibits a stagnant lid tectonic regime. This means that its lithosphere does not break into moving parts, but instead remains a single rigid shell. The lack of tectonic activity on Venus is attributed to its extreme surface conditions, with surface temperatures reaching approximately 900 degrees Fahrenheit and a dense atmosphere composed mainly of carbon dioxide. These conditions prevent the formation of the necessary thermal gradients and convection currents in the mantle that drive plate tectonics. Mars, on the other hand, provides a different perspective on planetary tectonics. Mars is smaller than Earth, with only about 1/3 of Earth's gravity and a colder internal structure. These factors contribute to the absence of active plate tectonics on Mars. The planet's surface shows evidence of volcanic activity and tectonic features from the past, such as the massive volcano Olympus Mons and the Valles Marineris Canyon system. However, these features are believed to be remnants of a bygone era when Mars was more geologically active. Today, Mars' lack of significant internal heat and a thinner atmosphere limit its tectonic and volcanic activity, rendering it a geologically dead planet. The absence of plate tectonics on Venus and Mars has profound implications for their habitability. Without plate tectonics, these planets lack the mechanisms for long-term climate regulation and nutrient recycling. On Earth, the carbon cycle driven by plate tectonics helps stabilize the climate over geological timescales, creating a stable environment for life to thrive. In contrast, the stagnant lid of Venus leads to a runaway greenhouse effect, while Mars' inactive geology results in a cold and barren landscape. The lack of plate tectonics on Venus and Mars suggests that the geological conditions necessary for sustaining complex life are not common. If other potentially habitable planets in the galaxy also lack tectonic activity, they may also be less likely to support advanced civilizations. The scarcity of geologically active planets could be a significant factor in explaining the apparent silence of the cosmos. Earth wasn't always this geologically active. Initially, it had a stagnant lid like Venus. Over billions of years, increased internal heat and tectonic stresses caused the crust to fracture into plates. This transition to active plate tectonics coincided with the emergence of complex life, suggesting a deep connection between Earth's geology and biological evolution. Earth was a very different place from the planet we know today. In its infancy, Earth's surface was dominated by a stagnant lid, similar to what we observe on Venus today. This meant that the lithosphere was a single unbroken shell with minimal tectonic activity. However, as the planet cooled and its internal heat accumulated, the lithosphere began to break into plates. This transition marked the beginning of plate tectonics as we understand it. The shift from a stagnant lid to active plate tectonics was a gradual process, driven by several key factors. One of the most important was the accumulation of internal heat from radioactive decay and residual heat from the Earth's formation. This heat created convection currents in the mantle, which exerted stress on the overlying lithosphere. Over time, these stresses caused the lithosphere to crack and form distinct plates that could move independently. Another crucial factor in the development of plate tectonics was the presence of water. Water acts as a lubricant, reducing the viscosity of the mantle and facilitating the movement of tectonic plates. The presence of large oceans on Earth likely played a significant role in promoting the formation and movement of tectonic plates. Water also contributes to the weakening of the lithosphere by promoting the formation of subduction zones, where one plate is forced beneath another, driving the recycling of the lithosphere into the mantle. The timing of the transition to active plate tectonics is closely linked to the emergence of complex life on Earth. Geological evidence suggests that significant tectonic activity began around 3 billion years ago, roughly coinciding with the rise of multicellular organisms. This correlation suggests that the development of plate tectonics may have created the conditions necessary for the evolution of complex life. The Drake equation is a formula used to estimate the number of advanced civilizations in the galaxy. Traditionally, it includes factors like star formation rates and the likelihood of planet formation. By incorporating geological factors, we can refine these estimates. Planets with active plate tectonics might be rare, making complex life even less common than previously thought. The Drake equation, formulated by astronomer Frank Drake in 1961, seeks to quantify the number of technologically advanced civilizations in the Milky Way galaxy with which we might communicate. The equation considers several factors, including the rate of star formation, the fraction of stars with planetary systems, the number of planets per star that could potentially support life, the fraction of planets where life actually develops, the fraction of planets with intelligent life, the fraction of civilizations that develop detectable technologies, and the length of time such civilizations release detectable signals into space. Traditionally, the Drake equation is focused on astronomical and biological factors, assuming that the development of life is primarily influenced by the availability of suitable conditions such as liquid water, appropriate temperatures, and a stable atmosphere. However, recent research suggests that geological factors, particularly the presence of plate tectonics, play a crucial role in creating and maintaining habitable conditions. By integrating geological considerations into the Drake equation, we can gain a more nuanced understanding of the likelihood of finding advanced civilizations. One of the key geological factors to consider is the role of plate tectonics in regulating a planet's climate. The carbon cycle, driven by tectonic activity, helps stabilize atmospheric carbon dioxide levels and maintain a relatively stable climate over geological timescales. Without this regulatory mechanism, a planet's climate could become too extreme for complex life to thrive. By incorporating the presence of active plate tectonics into the Drake equation, we can refine our estimates of the number of planets that maintain stable, habitable climates. Another important consideration is the recycling of nutrients through tectonic processes. The constant renewal of the planet's surface ensures that essential nutrients remain available to living organisms. Planets without active tectonics may lack the necessary nutrient cycling to support complex ecosystems, limiting the potential for the development of advanced life forms. Including nutrient recycling as a factor in the Drake equation allows for a more accurate assessment of a planet's ability to sustain complex life. The creation of diverse habitats through tectonic activity also plays a significant role in promoting biodiversity and evolutionary innovation. The formation of mountains, islands, and ocean basins generates a variety of ecological niches, providing opportunities for different forms of life to evolve and adapt. This diversity is crucial for long-term sustainability of complex ecosystems and the development of advanced civilizations. By accounting for the role of tectonics in creating diverse habitats, we can better estimate the number of planets with the potential for complex life. Incorporating geological factors into the Drake equation highlights the rarity of planets with the right conditions for sustaining complex life. If active plate tectonics are essential for maintaining habitable conditions, then the number of planets capable of supporting advanced civilizations, may be much smaller than previously thought. This rarity could help explain the apparent silence of the cosmos and provide a possible solution to the Fermi paradox. Scientists are now on the lookout for exoplanets that exhibit signs of plate tectonics. Missions like the James Webb Space Telescope and others aim to detect signs of geological activity on distant worlds. By analyzing the atmospheres and surfaces of exoplanets, researchers hope to identify those with the potential for complex life. The search for exoplanets with active geological processes is a rapidly advancing field, driven by new technologies and innovative observational techniques. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up exciting possibilities for finding habitable worlds. To date, thousands of planets have been identified, with a significant number located in the habitable zone of their parent stars, where conditions might be right for liquid water to exist. One of the key challenges in identifying exoplanets with plate tectonics is the detection of geological activity from vast distances. Traditional methods of exoplanet detection, such as the transit method and radial velocity measurements, provide information about the planet's size, mass, and orbit, but offer limited insights into geological characteristics. To overcome this challenge, scientists are developing new techniques to analyze the atmospheres and surfaces of exoplanets for signs of tectonic activity. The James Webb Space Telescope, JWST, represents a significant leap forward in our ability to study exoplanets. Equipped with advanced instruments capable of analyzing the composition of exoplanetary atmospheres, JWST will search for signatures of gases associated with geological processes, such as volcanic outgassing. The detection of certain gases, such as sulfur dioxide and carbon dioxide, in an exoplanet's atmosphere could indicate active volcanism and tectonic activity. Another promising approach involves studying the thermal emissions of exoplanets. Planets with active tectonics and volcanic activity emit heat, which can be detected using infrared observations. By analyzing the thermal signatures of exoplanets, scientists can identify those with higher surface temperatures indicative of geological processes. This method, combined with atmospheric analysis, provides a comprehensive picture of an exoplanet's geological activity. In addition to direct observations, researchers are also using computer simulations and models to predict the likelihood of plate tectonics on exoplanets. By inputting data on a planet's size, composition, and orbital characteristics, scientists can simulate its internal dynamics and assess the potential for tectonic activity. These models help prioritize targets for observational campaigns and refine our understanding of the conditions necessary for plate tectonics to occur. The search for exoplanets with plate tectonics is not limited to current missions. Future space telescopes, such as the European Space Agency's Ariel mission and NASA's Habitable Exoplanet Observatory, HABEX, are designed to provide even more detailed observations of exoplanet atmospheres and surfaces. These missions will build on the capabilities of JWST, allowing for more precise measurements of geological activity and the identification of habitable exoplanets. The detection of exoplanets with active plate tectonics would be a significant milestone in the search for extraterrestrial life. Such planets would likely have stable climate, nutrient recycling, and diverse habitats, increasing the chances of finding complex life forms. Identifying these planets would also provide valuable targets for future missions aimed at direct imaging and characterization of exoplanetary surfaces. In the context of the Fermi paradox, the search for exoplanets with plate tectonics addresses one of the key factors that may influence the development of advanced civilizations. If the presence of active geological processes is rare, It could help explain the apparent scarcity of intelligent life in the galaxy. By focusing our search on planets with the right geological conditions, we increase our chances of finding habitable worlds and potentially answering the profound question of whether we are alone in the universe. As we continue our search for extraterrestrial life, understanding the role of geological activity becomes ever more crucial. The geological solution to the Fermi paradox suggests that complex life requires specific and rare conditions. Future discoveries will hinge on our ability to find planets with the right geological characteristics. The search for extraterrestrial life is one of the most profound scientific endeavors of our time. It challenges our understanding of the universe and our place within it. As we explore the cosmos, we must consider the critical role that geological processes play in creating and maintaining habitable conditions. The geological solution to the Fermi paradox provides a compelling framework for understanding why advanced civilizations may be rare. The future of the search for extraterrestrial life will involve a multidisciplinary approach, combining insights from astronomy, geology, biology, and planetary science. Advanced space telescopes such as the James Webb Space Telescope and future missions like Ariel and Hoag will provide unprecedented capabilities for studying exoplanets. These instruments will help us detect and analyze the geological and atmospheric conditions of distant worlds in scientists' search for signs of tectonic activity and other indicators of habitability. The discovery of exoplanets with active plate tectonics would revolutionize our understanding of planetary habitability. Such planets would likely have stable climates, diverse ecosystems, and the necessary conditions for complex life to thrive. Identifying these planets would provide valuable targets for future missions aimed at direct imaging and in-depth characterization of exoplanetary surfaces and atmospheres. In addition to observational missions, the search for extraterrestrial life will benefit from advancements in computational modeling and simulations. By refining our models of planetary formation, evolution, and geological processes, we can better predict which exoplanets are likely to have active tectonics. These models will help guide our observational efforts, allowing us to prioritize our most promising targets. As we look to the future, international collaboration will be essential in advancing the search for extraterrestrial life. Coordinating efforts between space agencies, research institutions, and scientists from diverse disciplines will enhance our ability to explore the cosmos. By sharing data, resources, and expertise, we can accelerate the pace of discovery and increase our chances of finding evidence of life beyond Earth. The potential discovery of extraterrestrial civilizations would have profound implications for humanity. It would challenge our understanding of biology, technology, and our place in the universe. The search for extraterrestrial life is not just a scientific pursuit. It is a quest to answer fundamental questions about existence, intelligence, and our place in the cosmos. The geological solution to the Fermi paradox suggests that the conditions necessary for sustaining complex life are more stringent than previously assumed. The presence of plate tectonics, with its associated benefits for climate regulation, nutrient recycling, and habitat diversity, may be a key factor in determining a planet's habitability. As we continue to explore the cosmos, understanding the importance of geological processes will be crucial in guiding our search for extraterrestrial life. The future of this search holds the promise of groundbreaking discoveries that will reshape our understanding of the universe and our place within it. Have you ever heard of a galaxy that defies categorization? Imagine a cosmic structure that combines an ancient dormant core surrounded by a bright halo of young stars. This is not your typical spiral or elliptical galaxy, but something much more mysterious: a Hoag object. Initially mistaken for a planetary nebula or gravitational lens, the true nature of Hoag's object remained hidden until more advanced observations revealed its unique structure. The central elliptical core appears red and inactive, while the outer ring is bright blue, teeming with new star formation. A clear gap separates the two components as if they belong to different galaxies. The object spans an impressive 121,000 light-years wide, with a central core about 17,000 light-years across and an outer ring stretching out 75,000 light-years. This apparent gap between the core and the ring is wider than the ring itself, which is a surprising feature for such a colossal galaxy. Ring galaxies, like Hoag's object, are extremely rare, making up less than 0.1% of all known galaxies. They often arise from complex cosmic events, but Hoag's object seems to maintain a calm and orderly appearance, which further deepens the mystery. Despite decades of research, astronomers are still grappling with the question of the origin of this galaxy. Was it the result of a quiet accretion process, or did a cosmic collision play a role? Arthur Hoag, a prominent astronomer of the mid-20th century, made a discovery that would intrigue and puzzle scientists for decades to come. In 1950, while conducting a study of the night sky, the astronomer came across a celestial object that defied conventional classification. This object, later named after him, had characteristics unlike any previously observed galaxy. At first glance, Hoag's object appeared to be a planetary nebula, a cloud of gas and dust surrounding a dying star. However, its unusual structure, consisting of a central core surrounded by a luminous ring, suggested otherwise. Early images taken by the astronomer's telescope showed a clear separation between the inner and outer components, prompting curiosity and speculation. Initial hypotheses varied widely. Hoag himself hypothesized that it could be a planetary nebula, or even a gravitational lens. The gravitational lens hypothesis suggested that the object was not a galaxy at all, but rather a massive elliptical galaxy magnifying a background galaxy in a ring-like shape. Gravitational lenses occur when a massive object, such as an elliptical galaxy, bends the light of a more distant object behind it. This bending creates a ring of light around the foreground object, known as the Einstein ring. In early observations, the outer ring of Hoag's object resembled such a lens, suggesting that it may be a foreground galaxy amplifying the light of a more distant object. For nearly 4 decades, the true nature of the Hoag object remained uncertain. It was not until 1987 that astronomers equipped with better technology were able to confirm the connection between the ring and the nucleus through spectroscopic analysis of the red shift. This shift is due to the expansion of the universe, with more distant objects exhibiting a greater redshift. By analyzing the redshift of the core and ring of Hoag's object, astronomers confirmed that they're not separate entities, but components of the same galaxy. This discovery debunked the gravitational lens hypothesis and cemented the status of the Hoag object as a unique type of galaxy. The central core, consisting of old red stars, contrasts sharply with the outer ring, which is bright blue and actively forming new stars. It is this special composition and structure that distinguishes Hoag's object from typical spiral and elliptical galaxies. Ring galaxies are rare, making up less than 0.1% of all known galaxies. Typical spiral galaxies have sprawling arms of stars, while elliptical galaxies have a more uniform, rounded shape. The Hoag object, with its perfectly separated nucleus and ring, remains one of the most well-defined examples of this rare class of galaxies. The discovery began the scientific journey to understand one of the most mysterious structures in the universe. Today, with the help of modern telescopes and ongoing research, astronomers are trying to unravel the mysteries surrounding this fascinating cosmic anomaly. Its quiet appearance, distinct breakup, and combination of an ancient core with a young, star-forming ring make object Hoag a unique and enigmatic galaxy, prompting astronomers to investigate various theories of its origin and evolution. Thus, one of the main theories proposed to explain the formation of the Hoag object is the collision hypothesis. According to this theory, the characteristic ring structure of the galaxy arose as a result of a high-speed collision of a smaller galaxy with a larger one. When a smaller galaxy collides with a larger galaxy, the impact generates a density wave that rushes outward from the center of the larger galaxy. This wave compresses the interstellar gas, causing star formation in the ring around the galaxy's nucleus. The Cartwheel galaxy, with its strikingly similar ring structure, is a classic example of this process. In the case of a Hoag object, if a smaller galaxy collided with it, we would expect to detect several key features. First, the collision would create density waves that push the gas and stars outward, forming a ring. Moreover, the stars in the ring should have exhibited high relative velocities, indicating the kinetic energy from the collision. And third, in or near the ring, there would be residual fragments or remnants of colliding galaxies. However, detailed observations of Hoag's object have revealed some inconsistencies with the collision hypothesis. The ring stars do not exhibit the high relative velocities that are usually associated with such events. In addition, there's a notable absence of residual fragments or evidence of a second galaxy. To test this hypothesis, models of galaxy collisions have been used. These models show that, although a collision may produce a ring structure, the resulting galaxy often retains traces of violent interaction. The Hoag object, which has a calm and symmetrical appearance, lacks these chaotic features, suggesting a more complex formation history. However, another intriguing possibility looms on the horizon: resonance theory. Could a galaxy's ring structure be the result of gravitational interactions within a spiral galaxy? Let's explore this question. Another fascinating theory explaining the formation of the Hoag object is the resonance theory. According to this theory, the ring structure of a galaxy can arise as a result of the internal dynamics of barred spiral galaxies, in particular due to resonance in the gravitational field. Spiral galaxies are characterized by the structure of a central bar, from the ends of which spiral arms branch off. These bars play a crucial role in the dynamics and evolution of the galaxy. According to theory, as the bar rotates, it can create a resonance that affects the distribution of gas and stars within the galaxy. Resonance occurs when gravitational forces within a galaxy create regions in which the rotational velocities of stars and gas clouds synchronize. These regions can trap gas and stars, resulting in the formation of rings. There are several basic types of resonances. Inner Lindblad resonance occurs near a galaxy center, often forming an inner ring. Outer Lindblad resonance arising further, potentially forming an outer ring. The third type is co-rotation resonance, a region where the rotational velocity of the bar coincides with the orbital velocity of the stars and gas, which can also lead to ring formation. In the case of the Hoag object, the presence of a ring around the elliptical core suggests that such resonances may have played a role in its formation. The bar structure could have caused a resonance that trapped gas and stars at certain radii, creating the distinct ring we see today. When the bar rotates, it exerts a gravitational influence that can reorganize the gas and stars of the galaxy. Over time, this process can lead to the formation of a well-defined ring structure. Resonance theory provides a mechanism for how a spiral galaxy can evolve into a ring galaxy without a collision. NGC 1291 is a classic example of a galaxy in which resonance effects likely played a role in ring formation. The central band and outer ring provide a visual analogy of what may have happened in Hoag's object. However, the resonance theory faces difficulties when applied to the Hoag object. In particular, the Hoag object currently has no central bar. This absence raises the question of whether the bar may have existed in the past and subsequently dissipated, or whether other processes may have contributed to the formation of the ring. However, there is another interesting and equally plausible theory: the accretion theory. Can the gradual accumulation of intergalactic gas explain the unique structure of the galaxy? Let's explore this in more detail. The third major theory proposed to explain the formation of the Hoag object is the accretion theory. According to this theory, the unique structure of the galaxy resulted from the gradual accumulation of intergalactic gas, rather than from a dramatic collision or internal resonance. Accretion is the process by which a galaxy collects gas from the surrounding intergalactic medium over a long period of time. This gas is entrained by gravitational attraction, gradually accumulating and forming new structures. In the case of the Hoag object, it's likely that a central elliptical core formed first. Over time, the gravity of this core attracted gas from the intergalactic medium. As the gas approached the nucleus, it began to rotate around it, forming a ring structure due to angular momentum conservation. As gas accumulated in the ring, its density reached a high enough density to trigger star formation. This process explains the bright blue color of the ring, indicating active, ongoing star formation. And the gap between the core and the ring is explained by the balance of gravitational forces and the dynamics of the infalling gas. Galaxies such as NGC 6028 provide an example of how accretion can lead to the formation of ring structures. These galaxies show similar features: older central nuclei and younger rings of star-forming regions, which supports accretion theory as a plausible explanation. While the accretion theory provides a plausible explanation, it also raises questions. Why does the ring form at a particular radius? How did the dynamics of gas influx and star formation balance create such a clear separation between the core and the ring? These questions continue to drive research and exploration. Continued observations have provided evidence to support this theory. The ring of Hoag's object contains more gas mass than the entire Milky Way, suggesting significant accretion of intergalactic material. In addition, the well-defined structure of the ring and the absence of chaotic remnants are consistent with a gradual and orderly accretion process. Recent research has also significantly deepened this theory. By modeling the gravitational interaction in such ring systems, scientists have shown how the balance of forces can create stable and unstable orbits, leading to discontinuities in the distribution of matter. These results are consistent with the observed structure of the Hoag object, where the gap between the core and the ring is a region of unstable circular orbits, further supporting the theory. Also, the accretion theory offers a quite convincing explanation for the formation, suggesting that the galaxy grew and evolved through the slow accumulation of surrounding gas. This process contrasts with the more violent and destructive events described in the collision and resonance theories. However, each of these proposed theories, collision, resonance, and accretion, has their own flaws, leaving several unanswered questions. Although the collision hypothesis explains the formation of the ring by density waves created by galaxy collisions, it does not explain the ordered structure of the object and the absence of residual fragments and high relative velocities commonly observed in such events. Resonance theory, on the other hand, suggests that internal gravitational resonances within a twisted spiral galaxy can create ring structures. However, it's clear that Hoag's object lacks the central bar necessary for this process, and the theory does not fully explain the apparent gap between the nucleus and the ring. Accretion theory, in turn, argues that the gradual accumulation of intergalactic gas forms a ring. While this explains the ordered structure and ongoing star formation, questions arise as to why the ring forms at a particular radius, and how the dynamics between the core and the ring create such a distinct gap. Despite these theories, several mysteries remain. Why is there a significant gap between the nucleus and the ring? What specific conditions led to the formation of such a well-defined structure? And how do gravitational forces and dynamics within the galaxy interact to maintain this balance? Future telescope missions, such as the Nancy Grace Roman Space Telescope and the soon-to-be-launched Extremely Large Telescope, are designed to provide a deeper understanding of such questions. These advanced observatories will provide higher resolution images and more detailed spectroscopic data, potentially revealing the processes underlying the formation of such ring galaxies. As we explore the cosmos, Hoag's object remains a testament to the diverse and complex processes that form galaxies, and remind us once again that there are still mysteries in the cosmos waiting to be discovered. Are we alone? This question is in some ways as old as the starlight that travels through the eons to reach us. Since the earliest civilizations, our ancestors have looked up at the night sky in wonder, their imaginations fired by the flickering lights overhead. Today, armed with the power of modern science and technology, we still await the answer to this age-old question. But our goal is not just to find primitive life, but to discover the whispers of civilizations that might share this grand cosmic stage with us. The Breakthrough Listen Project, the most ambitious search for these whispers, techno-signatures, is pushing the limits of our hearing in an attempt to capture the murmurs of extraterrestrial life. As we stand at this crossroads of discovery, several teams of scientists in the Breakthrough Listen study and other SETI projects have already published several scientific papers moving us closer to answering this question. So, how close are we to the goal in this grand quest? What non-trivial decisions have been made to ensure a seamless search for signals and improve our chances? Let's get to the bottom of it. In our celestial odyssey to unlock the mysteries of life beyond Earth, scientists have charted two major paths across the cosmic seas: the search for biosignatures and the search for technosignatures. Each path offers a unique lens through which to view the potential for life in the universe, guided by the principles of astrobiology and the advanced technologies at our disposal. Biosignatures, the chemical fingerprints of life, serve as beacons in our search for biological activity on distant worlds. These signatures are not just markers, but signs of complex interactions between living organisms and the environment. Every molecule, from the oxygen and ozone created by photosynthetic life forms to the methane and carbon dioxide produced by biological and geological processes, carries a story of potential life. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to the infrared spectrum, is our most advanced scout in this endeavor. Using transmission spectroscopy, JWST can analyze, dissect light from distant stars as it passes through the atmospheres of orbiting exoplanets. This light bears the fingerprints of various molecules, each absorbing certain wavelengths and leaving behind a spectral signature that JWST can detect and analyze. Peering into the depths of space, JWST searches out these spectral lines with precision, allowing us to infer the presence of water vapor, carbon dioxide, methane, and other potential biosignatures in the atmospheres of exoplanets. This method not only hints at the possibility of life, but also provides insight into the atmospheric composition, climate, and habitability of these distant worlds. Parallel to the search for biosignatures is the search for technosignatures, the hallmarks of advanced technological civilizations. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap to complexity, where life has evolved to use and manipulate its environment in profound ways. From radio signals to megastructures orbiting distant stars, technosignatures embody the potential to detect not only life, but also societies that may have mastered the art of cosmic communication. The pursuit of technosignatures spans the galaxy. Initiatives like the Breakthrough Listen project utilize vast networks of radio telescopes to listen to and eavesdrop through space. These telescopes scan the sky for narrowband radio signals, anomalies in the natural cosmic radiophone that may indicate deliberate transmissions from intelligent beings. Biosignatures are whispers of life embedded in the fabric of a planet's atmosphere, providing a glimpse into invisible worlds orbiting distant stars. Among the vast number of potential biosignatures, 4 stand out for their significance: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and mysterious unexpected combinations of molecules. Oxygen, the breath of life on our planet, and its companion, ozone, form the first pair of key biosignatures. On Earth, oxygen is a byproduct of photosynthesis, the process that formed our atmosphere and allowed life to thrive. The presence of ozone, a molecule formed from oxygen by the sun's ultraviolet radiation, provides a protective layer shielding the surface from harmful radiation. The discovery of these molecules in the atmosphere of an exoplanet could indicate the presence of a thriving biosphere, perhaps similar to our own. Phosphine and ammonia, less common but no less intriguing, represent a second pair of biosignatures. Phosphine, a gas associated with anaerobic ecosystems on Earth, has been proposed as a potential marker of biological activity on other planets. Ammonia, another molecule with biological ties, may indicate the presence of life, especially in environments where it's not expected to exist in significant quantities due to non-biological processes. Methane and carbon dioxide form the third cornerstone of our quartet of biosignatures. Methane, a potent greenhouse gas, can be produced both biologically by organisms such as methanogens and abiotically by geologic processes. Carbon dioxide, a critical component of Earth's carbon cycle, is a product of respiration and volcanic activity. The simultaneous presence of methane and carbon dioxide, especially in unexpected ratios, may hint at biological processes in nature. Finally, with the fourth point, we move into the realm of unexpected combinations of molecules, methane and carbon dioxide, which cannot be stably present in more or less large quantities simultaneously without being transformed into other substances. Such combinations defy conventional expectations and point to the possibility of life functioning based on alien biochemical processes. The James Webb Space Telescope, JWST, humanity's most advanced observatory, is designed to study the atmospheres of exoplanets in search of these very biosignatures. Using transmission spectroscopy, JWST studies light from a star as it passes through a planet's atmosphere during its transit. When light passes through atmospheric gases, certain wavelengths are absorbed by the molecules, leaving behind a spectral fingerprint that JWST can detect and analyze. On the other hand, technosignatures, like the fingerprints of advanced civilizations, offer a different path in our quest to discover not just life, but societies that have reached a level of technological sophistication, perhaps similar to or even superior to our own. Unlike biosignatures, which hint at the mere presence of life, technosignatures speak of the ability of civilizations to alter the environment on a grand scale, communicate across the stars, and harness energy in ways we're only beginning to imagine. Technosignatures cover a wide range of signals and structures, from radio waves unintentionally emitted by a planet's communication networks to deliberate beacons aimed at the stars, from colossal energy collectors known as Dyson spheres to the barely perceptible glow of city lights on the exoplanet's night side. These signatures, if detected, will not only indicate the presence of life, but will also provide deep insights into the technological capabilities of alien civilizations. Our own planet is a prime example of a world teeming with technosignatures. Every radio broadcast, every satellite, and every piece of space debris orbiting the Earth creates a symphony of signals that, to the distant observer, unmistakably indicate the presence of an advanced civilization. The very fabric of our daily lives, from global communications networks to space probes venturing into the unknown, generates a cascade of signals that radiate out into space, making our presence known to all who can hear us. But why are technosignatures a more accurate way to search for technologically advanced civilizations? The answer lies in their specificity and the intentional or significant nature of the signals and structures they represent. While biosignatures can occur from simple microbial life to complex ecosystems, technosignatures clearly indicate a level of technological development and intent. The discovery of a technosignature not only confirms the existence of life, but also indicates that this life has crossed the threshold of cognitive and technological capability, engaging in activities that leave an indelible mark on the cosmic canvas. Breakthrough Listen was launched in 2016 with an ambitious mission to scour the cosmos for signs of technologically advanced civilizations. The project represents one of the most comprehensive searches for alien technosignatures ever undertaken. Armed with state-of-the-art technology and unprecedented scope, the project utilizes some of the most powerful radio telescopes in the world, including the Green Bank Telescope and Parkes Observatory. These colossal ears, tuned to the quiet whispers of the universe, can detect a range of signals, from faint radio emissions from distant stars to potential transmissions of extraterrestrial origin. At the heart of the mission is the desire to detect technosignatures, signals that, by their nature, can only be produced by technological means. These can range from narrowband radio signals that differ from the natural background noise of space to powerful laser pulses that cut through cosmic clutter. The project had previously focused on the Milky Way galaxy for strategic reasons, to begin the search in our cosmic neighborhood, where such signals may be strongest and most detectable. The Milky Way, with its billions of stars, provides fertile ground for such work. Each observable star is a potential sun for other planets. Each planet a potential cradle for life as we know it, or life yet to be imagined. The project was originally designed not just to search for signals in our galaxy, but to explore in depth the nature of life and intelligence in the universe. Sifting through the cosmic expanse of the Milky Way looking for signs of life is akin to searching for a single word spoken in a whisper in the middle of a bustling metropolis. A galaxy of about 100 billion stars can easily conceal the signals of other civilizations. The task of monitoring such a vast array of targets for technosignatures is monumental, not only because of the large number of stars, but also because of the complex array of cosmic phenomena that can obscure or the signals we are looking for. The problem is compounded by the limitations of our current technology and the limited resources at our disposal. Even with the most advanced radio telescopes, we can only listen to a small fraction of the stars in the galaxy at any given time. Huge distances dilute the signals, making them fainter as light years pass, and various natural cosmic phenomena such as the emission from pulsars and nebulae add further complexity to the search. In the face of these challenges, astronomers and scientists have looked beyond the familiar boundaries of the Milky Way to the wider universe. By observing galaxies as individual entities, each made up of billions of stars, we can try to pick up the cumulative signals of advanced civilizations. This extra-galactic strategy is based on the premise that a sufficiently advanced civilization can harness technologies that affect its entire galaxy, from building megastructures like Dyson spheres to harnessing the energy of supermassive black holes. Such grandiose endeavors could lead to technosignatures that, in theory, could be found in vast intergalactic voids. The transition to extragalactic studies comes with some challenges, from even greater distances to the need for more sensitive instruments and more sophisticated methods of data analysis. Nevertheless, each galaxy observed and each dataset analyzed brings us closer to understanding whether we're truly alone in the universe or part of a grander galactic world. Extragalactic exploration is exactly what Carmen Choza and her team did in 2023. Using the Robert C. Byrd Green Bank Telescope, the team has embarked on an ambitious mission to observe the centers of 97 nearby galaxies, studying them for 5 years. This work, one of the largest of its kind, used to search for narrowband Doppler drift in 4 frequency bands from 1 to 11 gigahertz. The goal was to detect signals that could come from civilizations capable of using energy equivalent to that of a Kardashev Type II civilization. The most important aspect of this study was the implementation of the SETI pipeline, a sophisticated tool designed to search for Doppler drift. This pipeline played a crucial role in analyzing the vast amount of data collected during the study. To combat the persistent problem of radio frequency interference, called RFI, which often mimics extraterrestrial signals, the team adopted an on-source, off-source cadence pattern. This method involves alternating between observations of a target galaxy, on-source, and a nearby region devoid of the target, off-source, and is repeated 3 times for each galaxy. Because RF interference and localized noise are present regardless of the telescope's pointing, they'll appear in both on-source and off-source observations. In contrast, a true astronomical signal should only manifest itself in observations from the source and not in the observations beyond the source. This approach helped to distinguish real astronomical signals from terrestrial interference, which improved the reliability of the results. Despite careful methodology and advanced technology, the study faced significant challenges, primarily due to radio frequency interference. The team's innovative radio interference mitigation strategies, including signal injection and recovery tests, were crucial in differentiating terrestrial and potential extraterrestrial signals. These efforts emphasize the difficulty of finding technosignatures, especially since signals must be significantly more powerful than those detectable within our galaxy to be considered extragalactic. The exhaustive search resulted in 6,034,313 hits across all observed galaxies. These matches represent cases where the data analysis pipeline has identified signals that potentially stand out from the background noise and may be of interest for further study. From the original 6,034,313 matches, further refinement and analysis using a computer algorithm narrowed the field to 1,519 events of particular interest. These events were then scrutinized by the research team, which attempted to distinguish potential extraterrestrial signals from the all-pervasive RFI noise. Despite the complexity, the team eventually concluded that all 1,519 events were associated with terrestrial sources, or natural cosmic phenomena. However, the work done by Chosa and her team not only illuminates the path we've traveled, but also beckons us to new horizons. The ability to reanalyze data through the subtle prism of machine learning promises us a chance to uncover signals that previously remained obscure or were perceived as noise. This changing landscape of SETI research, constantly enriched by technological innovation, invites us to look deeper. As we move forward, armed with improved tools and a deeper understanding of the challenges that await us, the search for extraterrestrial technosignatures continues. In the meantime, we'll be eagerly awaiting new opportunities to solve the mysteries of the cosmos. Amid the silent expanse of our solar system lurks a world of deep mystery and rugged beauty. Mars, with its purple dunes and ancient valleys, tells of its tantalizing past. It's a planet where sunsets color the sky blue, where towering dust devils run across the barren lands, and where the remnants of water streams silently tell the story of bygone days. Here, amid the red dust, lies the enigmatic brain terrain, a geologic marvel that defies explanation. Its intricate patterns, reminiscent of the complex folds of the human brain, remain one of Mars' most challenging mysteries. What forces created these enigmatic formations? Are they the key to unlocking the secrets of Mars' climatic past? As the sun dips below the horizon, the Martian sky transforms, casting blue light over the alien landscape. The scars of ancient rivers and cracks of dried mud tell a story of a time when water flowed freely on Mars, when the planet experienced the changing of seasons, and when this world may have been more Earth-like than we could have imagined. Yet for all of its wonders, Mars is a stark reminder of its alien nature. Today we'll travel to Mars, a world of beauty and mystery, a planet that holds the keys to our past and the promise of our future. Join us as we explore the mysteries of the good old red planet. Beneath the purple skies of Mars lies a canvas of geologic mysteries. Among them is the brain terrain. These complex patterns, reminiscent of the cerebral cortex, sprawl across the Martian mid-latitudes. Their origins are shrouded in mystery. What processes could have created such complex patterns? Scientists suggest that it's sublimation, the conversion of ice directly into vapor, that plays the key role here. Although the exact process remains cloaked in mystery, it's most likely the relentless interaction between the underground ice and the thin Martian atmosphere that forms the intricate patterns. But Mars is not a quiet world. It breathes and moves. Dust devils, those towering columns of cloying dust, rising kilometers into the rarefied atmosphere, are not just a spectacle of nature, but the architects of the Martian surface. They crisscross barren landscapes, leaving behind dark trails that testify to their passage. These ethereal giants, born from the interaction of heat and wind, reach more than 2 miles in height and are larger and more dramatic than their terrestrial counterparts. And then, as the Martian day fades, the sky transforms. A Martian sunset bathes the landscape in an ethereal blue light that contrasts sharply with the familiar red and orange hues of daytime. This phenomenon arises due to the unique interaction of sunlight with the atmosphere of the red planet, filled with dust of iron particles. As it passes through, the red part of the visible spectrum of sunlight is scattered by the dust particles, leaving only a mesmerizing blue glow. Although this scattered light colors the sky red, at sunset and night it transforms into shades of blue. But the mysteries of the Martian atmosphere don't end there. The interesting phenomenon of Mars' green glow, recently captured by NASA's Odyssey orbiter, provides a glimpse into the unique characteristics of the Martian atmosphere. This glow, observed from orbit, is the result of atmospheric processes that are common throughout the solar system, but manifest themselves differently on each planet due to variations in atmospheric composition and density. During the day, sunlight interacts with the Martian atmosphere, breaking down CO2 molecules through a process known as photodissociation. This releases individual atoms, which, when they hit the night side of the planet, recombine into different molecules while emitting light. On Earth, this phenomenon produces a whole spectrum of colors, but on Mars, the predominant color is green. This green glow is primarily due to the recombination of CO2 molecules in the upper atmosphere at an altitude of between 25 and 90 miles. Interesting studies have revealed an additional glow at lower altitudes, resulting from the recombination of oxygen atoms. This secondary glow, visible during the Martian summer, is concentrated in the polar regions, where atmospheric currents converge. The intensity of this glow varies with the time of year, alternating between the northern and southern hemispheres. The thinness of the Martian atmosphere compared to Earth's allows these luminous phenomena to be observed and studied more directly. It's also allowed the detection of other emissions, such as nitrogen oxide emissions in the ultraviolet spectrum, further enriching our understanding of the composition and behavior of the Martian atmosphere. Such atmospheric studies not only shed light on the processes that shape the Martian environment, but also provide valuable insights into the planet's past and present climatic conditions. Speaking of which, the Martian landscape, with its vast deserts and towering volcanoes, contains a wealth of clues about the planet's climatic past. Among them are signs of seasonal changes that have shaped the surface for millennia. The presence of features such as mud cracks, discovered by the Curiosity rover, which bear a striking resemblance to similar objects on Earth, suggests the presence of liquid water in the planet's past. In particular, the mud cracks are thought to have formed over many Martian seasons, indicating a cycle of wet and dry periods that Mars once experienced. Further evidence of Mars' dynamic climate can be found in the remains of ancient glaciers in the planet's mid-latitudes. These fossilized archives, imprinted into the Martian terrain, tell of a time when water ice slid across the planet's surface, carving furrows and transporting sedimentary rocks. These glaciers, like their terrestrial counterparts, shape the terrain, leaving behind traces of their presence in the form of moraines and carved valleys. Such activity suggests that Mars has undergone significant climatic changes, perhaps similar to the glacial and interglacial periods seen on Earth. The presence of sulfate in the mud cracks adds another layer to our understanding of Mars' water history. Mud cracks, like those found on Earth, are formed by the drying of sedimentary rocks, indicating the presence of standing water that periodically evaporates, leaving behind these prominent patterns or subsiding beneath the surface. The detection of sulfates in these formations indicates that water interacted with the Martian soil, resulting in the deposition of minerals. The varying levels of these sulfates, combined with the pattern of mud cracks, paint a picture of a planet where water levels rose and fell, creating conditions conducive to chemical reactions that could even support the precursors of life. Clearly, it's the search for water on Mars that is a key aspect in understanding the planet's climate, geologic history, and potential for habitable life. Recent discoveries have shed light on the presence of water in various forms and locations on Mars, significantly changing our understanding of the red planet. On Mars, there are a great many geologic features that indicate the presence of water in the past. The discovery of ancient lake beds, river valleys, and outflow channels indicates that at one time, water flowed freely across the planet's surface. These features suggest that Mars once had a warmer and wetter climate, capable of supporting liquid water on its surface. The presence of sedimentary layers and mineral deposits in these ancient lakes and river valleys further supports the idea of prolonged water activity that may have lasted thousands or even millions of years. One of the most revolutionary discoveries is the discovery of water ice near the equator of Mars. Traditionally, ice was thought to be found only in the polar regions of Mars, where it's visible on the surface. However, radar surveys and analysis have revealed subsurface deposits of ice at lower latitudes, including near the equator. This refutes previous ideas about the climate of Mars and suggests that water ice is much more widespread across the planet than previously thought. The implications of equatorial ice extend to the climate history of Mars and its potential habitability. Equatorial ice deposits indicate a more complex hydrologic cycle on Mars than previously thought. This could mean that in the past, Mars had a climate more similar to Earth's, with water cycling between the atmosphere and the surface. However, such a presence does not at all raise the possibility that conditions suitable for life existed on Mars in the past, much less in the present. Water is a key component of life, but such a contrasting climate change cannot offer much chance for a long process of development of any life forms. The search for biosignatures such as special minerals, organic molecules, or erosion patterns that may indicate past biological activity continues. Although no conclusive evidence of life on Mars has yet been found, the presence of water in various forms still retains a minimal possibility. Still, these water ice deposits could serve as a valuable resource for future human exploration and colonization of the planet, providing water for drinking, agriculture, and fuel production. Taking a closer look at the mineralogical landscape of Mars, we see that it's a stark contrast to the rich diversity found on Earth. About 6,000 different minerals have been discovered on our home planet, testifying to the dynamic geologic processes on Earth and the complex interaction between the biosphere and geosphere. These minerals have not only been formed by abiotic processes, but have also been significantly influenced by the presence of life, which has contributed to the diversity of minerals through various biochemical interactions. By comparison, after 5 decades of research, only 161 minerals have been identified on the Martian surface. This divergence in mineral diversity is not just a numerical gap. It tells us a lot about the differences in the geological activity and history of the two planets. The scarcity of minerals on Mars has profound implications for our understanding and the planet's potential to support life. The diversity of minerals on a planetary body is often a reflection of its geologic and environmental dynamism. On Earth, plate tectonics, water availability, and atmospheric processes contribute to the wide range of physical and chemical conditions that are so essential for the origin and maintenance of life. Complex organic molecules, including the precursors to DNA, often require diverse chemical environments and catalysts. The limited mineral diversity on Mars, therefore, raises some questions about the habitability of the planet as a whole. The lack of diverse minerals on Mars also indicates that the planet may have had a more monotonous geologic history compared to Earth. However, is it as quiet and peaceful as it appears? Recent studies of the internal structure of Mars have led to interesting discoveries, particularly through the analysis of seismic data. The InSight mission played a key role in this discovery before its completion, detecting what's believed to be the largest earthquake ever recorded on Mars. This earthquake, which lasted about 6 hours, did not fit the typical profile of a meteorite strike because no crater was left behind, suggesting it originated deep inside the planet. The magnitude of the quake, which was 4.7 on the Richter scale, hints at a significant geologic activity beneath the surface. Unlike Earth, Mars lacks plate tectonics, raising intriguing questions about the mechanisms causing these earthquakes. The lack of plate tectonics suggests that Martian earthquakes may be related to internal stresses or other geologic processes that we've not yet fully understood. Volcanic activity on Mars, both recent and ancient, has left indelible marks on its surface. Recent studies have found at least 40 different volcanic events, some of which occurred only a few million years ago. In addition, the discovery of unusual polygonal structures beneath the surface, found by ground-penetrating radar from China's Churong rover, indicates a history of thermal contraction and expansion and speaks to the planet's former volcanic activity. These structures, ranging in size from a few inches to a few feet, have been found at depths of about 100 feet. Obviously, a dramatic change in climate or some cataclysmic event has caused these deposits to be so deep beneath the planet's surface. The region known as Noctis Labyrinthus, with its vast network of valleys and canyons, is further evidence of Mars' volcanic past. Located near the volcanic Tharsis Plateau, home to the solar system's largest volcano, Olympus Mons. This region demonstrates the dramatic impact of volcanism on the Martian landscape. A video simulation provided by ESA shows how the stretching and bending of the Martian crust in this region, resulting in the formation of deep valleys and canyons, is evidence of the planet's active geologic past. The release of water during organic eruptions may explain the presence of ancient river valleys and lakes, providing a glimpse into times when Mars may have been more Earth-like, with a warmer and wetter climate. Understanding the planet's volcanic history not only sheds light on its past climate and potential for life, but also helps in future research, as regions with past volcanic activity may hold clues to the planet's habitability and the availability of vital resources. Speaking of livability, it's impossible not to mention the recent successes in the production of oxygen on Mars. The Mars Oxygen In Situ Resource Utilization Experiment, or MOXIE, was an achievement in space technology, successfully producing oxygen from Mars' carbon dioxide-laden atmosphere. Installed aboard NASA's Perseverance rover, MOXIE operates efficiently in a variety of Martian conditions, both day and night, and in different weather states of the planet's atmosphere. Its ability to convert CO2 into oxygen through the process of solid oxide electrolysis is a significant technological achievement. By heating the Martian atmosphere to 800 degrees Celsius, MOXIE decomposes CO2 into oxygen ions and carbon monoxide, and then recombines the oxygen ions into breathable O2. This process has been shown to achieve the required oxygen production and purity despite design trade-offs due to the mass, power, volume, and cost constraints associated with space missions. The success of MOXIE has profound implications for the future of human exploration and potential colonization of Mars. The ability to produce oxygen on Mars paves the way for a sustainable human presence, reducing dependence on Earth for critical life support resources. The study concludes that a large-scale version of MOXIE could generate tens of tons of oxygen, essential not only for astronauts' life support, but also as a critical component of rocket fuel. Such a capability would significantly reduce the logistical and financial burden of transporting oxygen from Earth to Mars, which would otherwise require launching hundreds of tons of the material into space at an exorbitant cost. By providing a reliable supply of oxygen, systems like MOXIE could support longer missions, larger crews, and even permanent settlements on Mars. In addition, the technology can be adapted to produce other necessary resources, such as water and fuel, taking a significant step toward realizing the dream of a self-sufficient human presence on the Red Planet. Speaking of the Perseverance rover, we should also mention its Ingenuity helicopter, which has far exceeded the original parameters of its mission on the Martian surface. Built just for a brief technology demonstration, Ingenuity was only supposed to make 3 flights within 30 days. However, it shattered those expectations by flying 72 missions over more than 1,000 Martian days, demonstrating its resilience and adaptability to the harsh Martian environment. This achievement was not only an important milestone in the aerial exploration of other planets, but also laid the groundwork for future missions. Ingenuity's journey was not without its challenges. It encountered and overcame numerous technical problems, including communication outages and unexpected landing scenarios. Despite these challenges, Ingenuity continued to push the limits of what was possible and even set a new range record on one of its flights. The vehicle's ability to survive and operate through Martian dust storms, extreme temperatures, and even sensor failure speaks to the reliability of its design and the team's careful planning. However, the mission ended in an unforeseen way when a significant part of the blade of one of Ingenuity's rotors was damaged, making further flight impossible. This incident marked the official end of Ingenuity's Mars mission. The helicopter's final flight took place in January 2024. However, the termination of Ingenuity's missions does not take away from its outstanding achievements and the invaluable data it provided. NASA has already begun applying lessons learned from operating aircraft in extraterrestrial environments to upcoming missions, including the Dragonfly mission to Titan, Saturn's largest moon. The success of Ingenuity has opened the door to more ambitious use of aircraft for tasks such as sample retrieval, which could significantly increase the efficiency and scope of exploration of other planets. During its long stay on the Red Planet, the Perseverance rover has accumulated a considerable amount of samples of Martian rock materials. However, it's worth noting that the endeavor to return samples from Mars to Earth is both the pinnacle of scientific endeavor and the nadir of logistical challenges. The financial implications are staggering. According to recent estimates, the costs could exceed those of the most expensive space missions, such as the James Webb Space Telescope, totaling up to $11 billion. The complexity of safely extracting samples from the Martian surface and transporting them back to Earth involves multiple spacecraft and precise robotic operations. This task requires not only unprecedented precision engineering and navigation solutions, but also significant financial outlays, which raises questions about budget allocation and priorities in space exploration. When it comes to prioritizing space exploration, humanity faces another unresolved challenge. The ongoing debate over international cooperation in Mars exploration is multifaceted, involving political, scientific, and logistical considerations. On the one hand, cooperation can pool resources, share risks, and increase the scientific return on missions through diverse expertise. On the other hand, comparing the successes of collaborative efforts, such as the International Space Station, against the backdrop of some international constraints, highlights the contradiction between the ideal of a united human effort in space exploration and the reality of international relations on Earth. Another, but not the last, test in our path is that as Mars becomes a center of exploration and potential colonization, the problem of space debris is becoming increasingly important. Debris accumulation in Martian orbit can pose a hazard to spacecraft, impede navigation, and jeopardize missions. This problem is not just theoretical. The proliferation of debris around Earth has already created an urgent need for sophisticated tracking and avoidance maneuvers. In turn, solving this problem on Mars will require proactive measures to prevent the accumulation of debris, and possibly the development of debris reduction and removal technologies to ensure the safety and sustainability of future missions. Mars colonization, once the stuff of science fiction, is increasingly entering the realm of possibility, thanks to technological advances and scientific discoveries. The successful demonstration of in situ resource utilization through experiments such as MOXIE, the potential to use local materials for construction, and advances in life support systems are gradually laying the groundwork for a sustainable human presence on Mars. However, the vision for colonization goes beyond technological challenges to include ethical, social, and environmental considerations. The responsibility of extending humanity's footprint to another planet raises questions about how we steward the Earth and the extent to which we will be able to apply these lessons to the New World. The future of Mars exploration is rich in promise and fraught with challenges. As we stand at the threshold of these endeavors, the collective wisdom, ingenuity, and cooperative spirit of the global community will play an important role in overcoming these challenges and realizing the dream of expanding humanity's presence beyond Earth. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time, it governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomena. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways. But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. it's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. Wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of cosmos. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, Are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort space-time enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves. We explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? Humanity stands on the threshold of a new era, an era defined not only by exploration, but also by the bold dream of colonization. For decades, our gaze has been fixed on the familiar: the Moon, our celestial neighbor, and Mars, the red beacon in our night sky. These worlds, once the subject of science fiction, now beckon us with the promise of new frontiers. But beyond these well-trodden paths lies a world shrouded in mystery, a world that's changing our understanding of what it means to be a moon. This is Titan, Saturn's largest satellite. Titan is a world covered with a dense atmosphere, which is rare for a moon. It's a place where rivers and lakes flow not with water, but with liquid methane and ethane. Here, the sky is raining gasoline. And the cold is beyond anything that can be experienced on Earth. Yet, in this alien landscape lurks the potential for something extraordinary. Could Titan, a world so unlike our own, hold the key to our future in space? Could this distant moon hold the secrets to not only surviving, but thriving beyond our home planet?
It's one small step for man, one giant leap for mankind.
As we turn the pages of our history of space exploration, the Moon and Mars become beacons of human ambition. The Moon, our nearest celestial neighbor, has always been a constant companion in our night sky, a symbol of our desire to leave the confines of the planet. Mars, in turn, with its striking resemblance to Earth, fuels our dreams of finding a new home in space. Nevertheless, the Moon, despite its proximity, presents serious problems. Its surface is a barren wasteland, devoid of atmosphere and offering no protection from the harshness of space. The lunar environment is a vacuum, exposing astronauts to extreme temperatures and cosmic radiation. No atmosphere means no air to breathe, no wind to carry sound, and no sky to protect against the relentless barrage of solar and cosmic rays. Mars, though more Earth-like, is not without its own problems. Its thin atmosphere, consisting mostly of carbon dioxide, offers little protection from solar and cosmic radiation. The Martian environment is harsh and merciless, and temperatures at the poles can drop to minus 257 degrees Fahrenheit. The lack of a global magnetic field exposes the surface to the full force of the solar wind and cosmic rays. In contrast, Titan, Saturn's largest satellite, presents a very different environment. Shrouded in a dense atmosphere, Titan offers a natural barrier against the dangers of cosmic radiation. This atmosphere, richer in nitrogen than even the Earth's atmosphere, is the key to protecting future colonists from cosmic rays that mercilessly bombard less protected worlds such as the Moon and Mars. Titan's atmosphere isn't just a shield, it's a gateway to opportunity. Unlike the Moon and Mars, the air pressure on Titan's surface is 1.5 times higher than on Earth, creating a surprisingly familiar pressure environment for human explorers. This dense atmosphere opens up new possibilities for exploration and colonization, possibilities that are beyond the reach of our more trivial space goals. As we rethink our goals for space colonization, Titan becomes a compelling alternative, a world in which the atmospheric and radiation problems that limit our ambitions on the Moon and Mars become its strengths. Titan invites us to envision a future in which humanity can thrive under the protective embrace of an alien sky, a future in which the mysteries of this distant moon become stepping stones to our expansion into space. As we mentioned earlier, Titan, a moon of many mysteries, orbits around Saturn. Discovered in 1655 by Dutch astronomer Christian Huygens, Titan has captivated the imagination of scientists and dreamers ever since. This world is both similar to and in stark contrast to our Earth. Titan's environment is unlike anything else we've encountered in our solar system. It's the only known moon with a dense atmosphere, and the second largest moon in our solar system after Ganymede, a satellite of Jupiter. But it's not just the size that makes Titan stand out, it's the rich composition of its atmosphere and surface that really sets it apart. This moon is surrounded by a thick, nitrogen-rich atmosphere, similar in composition to Earth's, but far denser and more extensive. It's permeated with organic molecules, creating a kind of hazy orange glow that obscures the surface of the satellite from view. It's this nitrogen-dominated atmosphere that provides protection from solar radiation, which contrasts sharply with the barren sky of the Moon and Mars. Beneath this alien sky lies a landscape at once familiar and utterly alien. Titan's surface is formed by rivers and lakes, but they're not bodies of water as we know them. Instead, they're filled with liquid methane and ethane, flowing through channels carved into the Moon's icy crust. These hydrocarbon seas are a true marvel, a testament to the diversity of the universe's chemistry. The presence of these surface fluids is a key characteristic that distinguishes Titan from other celestial bodies. On Earth, the water cycle shapes climate and geography. On Titan, a similar cycle occurs, but the role of water is played by methane and ethane. This hydrocarbon cycle, with methane rain and ethane lakes, creates a dynamic environment that may provide clues to understanding the complexity of planetary atmospheres. So, by breaking the limits of our standard perception, we're slowly uncovering exactly what makes a planet or moon habitable. Its nitrogen-rich atmosphere and surface fluids open the door to new possibilities. Let's find out what they are. So the Moon's nitrogen-rich atmosphere provides a natural barrier against cosmic radiation, a major challenge for space colonization. Why do we pay so much attention to solar radiation? Well, the answer is simple, yet profoundly important. Solar radiation is a ruthless destroyer of living cells. It doesn't just affect microscopic life forms, it directly affects us as human beings. Unshielded exposure to solar radiation can cause severe cellular damage, destroying the very fabric of our biological existence. In space, spreading uncontrollably, this radiation poses one of the greatest threats to the survival and health of astronauts. On Earth, it's the atmosphere and magnetic field that protect us. On Titan, it's the dense nitrogen atmosphere that provides vital protection, making it a safer haven for future human colonists than the barren landscapes of the Moon or Mars. Beneath this protective dome is a world of liquid methane and ethane. These hydrocarbon lakes and rivers stand in stark contrast to the bodies of water we know on Earth, yet they offer intriguing possibilities. Imagine a world where boats sail on methane seas, where the familiar concept of the liquid cycle takes on a whole new form. The presence of these surface fluids is not just a curiosity, it's a resource. Methane and ethane have the potential to be used as fuel, providing energy for future colonies. This abundance of hydrocarbons makes Titan an attractive target for colonization, offering a solution to one of the biggest problems of space habitation: sustainable energy sources. But Titan's gifts don't end there. Beneath its icy surface lies another treasure: water ice. The very water so essential to human life is abundant on the satellite, trapped in its frozen crust. The presence of water ice, along with hydrocarbons, makes this moon a repository of vital resources, setting the stage for a self-sustaining human presence away from Earth. Titan, a world of incalculable potential, also presents enormous challenges. Severe cold, during which temperatures drop to minus 356 degrees Fahrenheit, creates an environment unsuitable for human life as we know it. In turn, Methane rain, a phenomenon unique to this moon, adds another layer of complexity to the survival equation. To overcome these challenges, we must turn to the pinnacle of human ingenuity and technology. Colonizing Titan will require not just adaptation, but a complete rethinking of human habitation in extreme conditions. Imagine dwellings designed to withstand low temperatures, insulated with materials yet to be invented, and harnessing the power of Titan's own resources to provide warmth and comfort. These habitats could be equipped with systems to convert atmospheric methane into heat, turning the problem itself into a resource for solving it. But survival is more than just keeping warm. Methane rain, while an obstacle, could turn into an advantage. Advanced collection and filtration systems could recycle methane not only as an energy source, but also as a raw material for essential commodities. Now, let's imagine a human colony on Titan. Imagine domed cities, their architecture a blend of science and art, designed to harmonize with Titan's unique environment. These structures, resistant to cold and methane rains, would be interconnected, forming a network, demonstrating human resilience in the face of alien conditions. Inside these domes, life thrives. Hydroponic gardens provide food, recycling systems conserve resources, and public areas foster a sense of community. It's a place where humanity has not just survived, but flourished, adapting decisively to Titan's challenges. Colonizing Titan is not just a distant dream. It's a future that beckons us to take up the challenge. With each technological breakthrough, with each bold leap of imagination, we come closer to making this alien world a new home for humanity. Watching the thriving human colony on Titan, it becomes clear that this moon is more than just a new home for humanity. It's a center of economic and scientific opportunity. The unique environment and abundant resources offer unprecedented prospects for both. The economic benefits of colonizing Titan are rooted in its vast hydrocarbon reserves. Key components of Titan's lakes and atmosphere are not only potential sources of energy, but also valuable raw materials for chemical synthesis. The ability to harness these resources could turn Titan into an economic center, meeting both the colony's needs and potentially supplying materials for interplanetary trade. Scientifically, Titan is a gold mine. Its complex atmosphere and surface chemistry offer unique research opportunities that offer insights into organic chemistry and astrobiology. Studying Titan's methane cycle and its prebiotic chemistry could unlock the secrets of the origin of life, not only on Earth, but potentially throughout the cosmos. Moreover, Titan's position in the solar system and its resources make it an ideal launching pad for future space exploration. Its low gravity and abundant fuel reserves could make it easier to launch spacecraft to distant destinations, making Titan a strategic outpost for exploring the outer solar system and beyond. However, with these opportunities come important ethical considerations. As we embark on the colonization of Titan, we must reflect on our responsibilities in interacting with the new world. Conservation of Titan's environment, respect for its unique characteristics, and thoughtful stewardship are paramount. We must approach Titan not as conquerors, but as custodians. How we relate to this world in the future will reflect our values and our ability to balance progress and responsibility. As we conclude our journey, let's reflect on the key points. A moon once shrouded in mystery has turned out to be a world full of potential. We explored the protective properties of Titan's nitrogen-rich atmosphere, a natural shield against the dangers of cosmic radiation. We traveled through alien landscapes where rivers and lakes of methane and ethane cut through icy terrain, offering resources that could secure our future in space. Our journey also took us to the potential of a vibrant human habitat, where ingenuity and resilience have turned challenges into opportunities. We saw how Titan's economy, driven by its abundant resources, can be a cornerstone of our interplanetary endeavors. As we ponder the future of humanity on Titan, we're reminded that colonization is not just about achieving technological perfection. It's a journey that forces us to grow, learn, and respect the universe we live in. So we leave you with a great question. What does this step mean for the future of humanity? How will our efforts on this distant moon affect our destiny in the vast, uncharted expanse of space? In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1 million miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus. allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogencation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. For years now, there's been a concept that defies the very laws of physics as we know them, a dream that has spawned countless stories and science fiction fantasies. This mystery is the search for a warp drive, a technology that could potentially allow us to travel vast distances in space faster than light itself. Imagine a journey where time and space constraints yield to the power of human ingenuity, where the farthest corners of the universe suddenly become accessible. This isn't just science fiction, it's a puzzle that scientists have been piecing together for decades, ever since physicist Miguel Alcubierre proposed a theoretical model in 1994. Alcubierre's model, a bold combination of imagination and Einstein's theories, offers a way to bend the fabric of space-time itself. But what lies behind this bold idea? Is it a mere flight of fancy? Or could it be the key to unlocking interstellar travel? Today we explore the tangled web of problems and breakthroughs surrounding warp drive. From the mysterious nature of negative energy to the tangled horizon problem. So let's dive into the depths of one of the most intriguing scientific quests of our time. The quest for the warp engine. Science or fiction? In the heart of Mexico City, amidst the hustle and bustle of city life, a young mind was fascinated by the mysteries of the cosmos. We're talking about Miguel Alcubierre. Born in 1964, a physicist whose name has become synonymous with one of the most innovative ideas in theoretical physics. His journey began in Mexico and led him to the prestigious University of Wales, where he delved deeply into the fields of general relativity and cosmology. In 1994, while working at the Max Planck Institute for Gravitational Physics in Germany, Alcubierre made a breakthrough in world perception that challenged our understanding of space travel. Inspired by the iconic science fiction series Star Trek, he posed a bold question. Could the laws of physics allow for a real warp drive? Let's break down the Alcubierre drive. Imagine a spaceship that does not move through space in the usual sense, but sits in a space-time bubble. This bubble, or deformation bubble, is the key to the Alcubierre concept. According to Einstein's general theory of relativity, massive objects distort the fabric of spacetime. Alcubierre hypothesized that if we could manipulate spacetime in a controlled way, we could create a warp bubble. The space in front of the bubble is compressed, pushing the bubble forward. Behind it, space expands, pushing it from behind. Inside this bubble, the spaceship remains stationary, but the bubble itself moves, allowing the ship to move faster than light without violating the laws of physics. This idea doesn't involve moving the spaceship at high speed. Rather, it's about moving space around it. It's like putting a surfboard, a spaceship, on a wave warp bubble and letting the ocean, space-time, carry it. However, the Alcubierre model is not simply a manipulation of space. It requires exotic matter with a negative energy density to stabilize the warp bubble. This exotic matter is one of the many theoretical obstacles scientists face as they try to turn the Alcubierre drive from a fascinating theory into reality. Delving deeper into the practical aspects of the Alcubierre drive, we're faced with huge challenges that stand between theory and reality. The first of these is the scale of energy and mass requirements. It was originally thought that creating a warp bubble would require an amount of energy equivalent to the mass of the observable universe, an unimaginably huge amount, far beyond our current technological capabilities. However, the field of theoretical physics is constantly evolving. An outstanding achievement was when physicist Chris Vanderbroek proposed modifications to the shape of the warp bubble. These adjustments dramatically reduced the energy requirement to about the mass of 3 suns. Still a colossal amount, but a significant step down from the original estimates. The second major obstacle is the need for exotic matter and negative energy. In the Alcubierre model, this exotic matter is crucial to stabilizing the warp bubble and making it function as intended. Negative energy is a peculiar and controversial concept. It's a concept in physics that can distort the very fabric of space-time. It's not just the absence of energy, but an actual physical quantity with negative characteristics. In the context of Alcubierre drive, negative energy will counteract the effects of normal positive energy, creating the conditions necessary for the existence and stability of the warp bubble. Negative energy, in the context of Alcubierre drive, is indeed a complex and somewhat elusive concept in physics, and it's important to distinguish it from the more familiar concepts of gravitational potential energy. In classical physics, the concept of negative energy often refers to gravitational potential energy. For example, the gravitational potential energy of an object in a gravitational field, like a planet, is considered negative energy because it takes work to move the object from the source of gravity to a point where this energy would be zero, for example, to infinity. This form of negative energy is the cornerstone of our understanding of gravitational interactions in the universe. However, the negative energy required for the Alcubierre drive is different. In this context, negative energy refers to a hypothetical form of energy whose energy density is less than zero. It's not just an accounting tool or a way of describing potential energy in a gravitational field, but rather a real physical substance or field with exotic properties, such as repulsive gravitational effects. This type of negative energy is not something we observe or well understand in the context of known physics. However, the existence of negative energy and, by extension, exotic matter remains a topic of intense debate and speculation in physics. Although phenomena such as the Casimir effect suggest the possibility of the existence of negative energy under certain conditions, harnessing it on the scale required for warp drive is a challenge. These challenges, the enormous energy requirements, and the need for exotic matter, underscore the monumental task of transforming Alcubierre drive from a theoretical model to a practical reality. They represent not just technological obstacles, but fundamental questions about the nature of the universe and our ability to manipulate its basic forces. As we move forward into the world of warp drive technology, we face another obstacle known as the Horizon issue. This issue is at the heart of the Alcubierre drive design and poses serious problems for its practical application. In astrophysics, the horizon is often referred to as the boundary beyond which events cannot affect an outside observer. The most famous example is the event horizon of a black hole, the point of no return. Beyond this horizon, the gravitational attraction is so strong that nothing, not even light, can leave it. Similarly, in Alcubierre drive, the horizon is the boundary of a warp bubble. Inside this bubble, the spaceship is cut off from the rest of the universe, just as the interior of a black hole is isolated from the outside world by its event horizon. The horizon problem arises from the unique structure of the warp bubble itself. In the Alcubierre model, the spacecraft is located in a region of the space-time plane surrounded by a warp bubble that compresses space at the front and expands it at the back. This manipulation of space-time allows travel at speeds faster than the speed of light, but with a critical limitation. It isolates the spacecraft from the rest of the universe. Imagine being inside this warp bubble, the very mechanism that allows you to travel vast distances in space also prevents you from controlling the ship or interacting with the outside world. Communication signals, navigation commands, and even visual observations are all prevented by the bubble's boundary. Passengers and crew will not be able to control the spacecraft, correct its course, or even stop the journey once it's begun. The implications of the horizon problem are profound. It implies that a spacecraft driven by warp would essentially be traveling on a one-way, uncontrolled journey. This raises practical questions about using such technology for exploration or travel. How do we get to specific destinations? How do we avoid collisions with celestial objects, or adjust our flight path to meet unforeseen circumstances? Moreover, this problem implies the need for a pre-established infrastructure, similar to an interstellar highway, with mechanisms to create and control the warp bubble from the outside. Such a requirement adds another layer of complexity to the already difficult task of realizing warp drive technology. While the horizon problem represents a significant engineering challenge, it is important to recognize that it doesn't invalidate the fundamental scientific validity of the concept. Theoretically, the principles underlying the warp drive remain unchanged and plausible within the framework of the general theory of relativity. As we delve deeper into the complexities of Alcubierre drive, we encounter another major problem: the radiation problem. This problem is twofold. It involves both the accumulation of radiation at the front of the deformation bubble and the potential effects of Hawking radiation within the bubble itself. First, let us consider the radiation accumulating at the front of the warp bubble. As the bubble moves through space at a speed faster than the speed of light, it inevitably encounters interstellar particles and cosmic radiation. These particles and radiation, unable to bypass the warp bubble, accumulate near its front end. Such accumulation poses a significant risk. When the warp bubble slows or stops, the collected radiation and particles will be released in a burst of energy. The intensity of this release could be catastrophic, not only endangering the spacecraft and its passengers, but potentially damaging any nearby objects at the destination. Moving inside the warp bubble, we encounter the second aspect of the radiation problem: Hawking radiation. This theoretical radiation, predicted by Stephen Hawking, arises from the effects of quantum mechanics near the edges of black holes. In the context of Alcubierre drive, the intense warping of space-time around the edge of the bubble could create conditions similar to those at the event horizon of a black hole, potentially generating Hawking radiation. This radiation could have harmful effects on passengers inside the bubble, exposing them to high levels of energy and particles. The implications of these radiation problems are profound. Not only do they pose serious engineering and safety challenges, but they also raise questions about the feasibility of long-duration travel using Alcubierre drive. Ensuring passenger safety and spacecraft integrity in the face of these radiation hazards is a critical area requiring further research and innovative solutions. It is a challenge that requires ingenuity and a deeper understanding of the interplay between quantum mechanics, the theory of relativity, and the harsh reality of space travel. When we turn our eyes to the current state of research in warp drive technology, we find ourselves in the thick of scientific research. Recent years have seen a flurry of theoretical papers and articles that break new ground in this field. One notable development has come from the work of physicists who've been revisiting the energy requirements of the Alcubierre drive. Based on earlier advances that significantly reduce the estimated energy requirements, recent papers have proposed various methods to further optimize the geometry of the warp bubble. These improvements are aimed at making the energy requirements even more feasible, approaching the realm of possibility. Significant contributions to the field have been made by researchers such as Harold White, who was instrumental in the experimental work on the feasibility of deformation bubbles and space-time manipulation at the NASA Eagle Works laboratories. Another area of active research is exploring alternative theories that could circumvent some of the limitations of the Alcubierre drive. For example, some physicists are exploring the possibility of using solitons, solitary waves that retain their shape while traveling at a constant speed, as a basis for creating stable strain bubbles without the need for negative energy. There's also growing interest in the role of quantum mechanics in warp drive physics. Researchers are delving into the quantum aspects of space-time and how they might affect warp drive mechanics. This includes studying the effects of quantum entanglement and the potential use of quantum fields to stabilize the warp bubble. Recent theoretical advances also include the study of the effects of warp drive technology on causality and the fabric of space-time. These studies are critical in addressing potential paradoxes and time travel scenarios, ensuring that the concept remains grounded in physical laws as we know them. Little by little, the dream of warp drive technology is moving ever closer from the pages of science fiction into the realm of scientific possibilities, driven by the tireless efforts of researchers around the world. As we ponder the future of warp drive technology, we find ourselves at a crossroad of assumptions and possibilities. The realization of warp drives, a concept once confined to the realm of science fiction, depends on several key developments and breakthroughs. First of all, the theoretical problems associated with warp drive technology need to be addressed. This includes finding viable solutions to the enormous energy requirements, the creation and stabilization of warp bubbles, and the safe management of radiation risks. Advances in areas such as quantum mechanics, exotic matter, and energy manipulation are critical to turning these theoretical possibilities into practical reality. Beyond the scientific and technical obstacles, the advent of warp drive technology brings with it many ethical and practical considerations. The ability to travel vast distances in space at unprecedented speeds would revolutionize space exploration, opening new horizons for humanity. However, with great power comes great responsibility. The ethical implications of such technology must be carefully considered. This includes the potential impact on space ecosystems, the responsibility to explore and possibly interact with extraterrestrial life, and equal access to this technology among nations and peoples. In practice, warp drive technology could lead to new methods of resource utilization, new ways of conducting scientific research, and even the possibility of interstellar colonization. This would fundamentally change our relationship with space, from one of exploration to one of habitation and utilization. For now, we look forward to a future in which stars are not just points of light in the night sky, but destinations within our reach. This future promises uncharted territories and unprecedented exploration, beckoning us to continue our quest for knowledge and discovery. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Pallidie is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the Sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the Sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the Sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the Sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto. a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS, like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies. Each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Auroras, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Auroras, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Auroras' formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts (NIAC) program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time, opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the 9th planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we place on it, but about embracing the diversity and complexity of the universe.